Okay, welcome back to another episode on the Delta potential. Today we're building a LIN network, so an automotive or a known automotive communication protocol, a local interconnect network, maybe. Anyways, we'll learn more about it, and sorry for my throat today. We'll learn more about it and take it all the way from concept to production. And here we'll focus a bit more on smaller components, one master and multiple slaves, but we will stick to two for the beginning, or maybe even just one for the beginning. And we'll add on that. So we'll make simple components, very similar in hardware, with some different sensors and actuators. So the master will be unique, while the slaves can be multiple slaves on the same network, maybe two of the same, and then an additional, who knows. But yes, so for anyone watching that has watched my streams before, I was up until recently working on an AC/DC switch mode power supply. Now I'm switching things up a little bit, starting with a new project that I really want to try. So basically make a LIN network. And hopefully it's interesting enough that we can continue with that. The AC/DC switch mode power supply is very interesting, but I'm a bit limited in what I can order right now and test. And if you've been watching that series, we made it up until the point where we could potentially order and test and everything, but it's not possible at the moment. So we will revisit that project later on. And maybe I will also do some preparation into what we can use it for. Maybe there's something we can add to it. And of course we can improve it and all that. And we, from that series, we got a good understanding of how an AC/DC switch mode power supply works. And we'll definitely use that in the future. But right now, we will start with the concept phase, and this will take some time. I mean, everything starts from an idea, and here I have one idea, and it's very simple. We're gonna make a network with a master that will monitor, perform diagnostics, making sure the whole network is operating as it should. And it should output, or at least keep track or control, show the end user some information that the slaves will be providing. So one of the slaves could be just outputting lights, for example, based on what the master decides, while the other slave could be operating or reading some sensor data and sending it continuously to the master in order for the master to output some information. So it's very, very simple, but working on these types of systems, you have to start with a good concept, good prerequisites, and you have to do proper system design, requirement handling, all that stuff if you're working with a customer or a supplier, depending on which side of the table you sit. But in this case, we're designing, we're building, we're doing the whole thing, and we'll also do some software in the future as well when we get these boards manufactured. and we can play around with it and then do some cool stuff. And I think it's, at least for me, feels good to work with communication protocol I know at least some about, but I would like to know more about it. And this is very simple, the LIN network. We'll also go into maybe a little bit more what the network is, and gather some information from the internet on that, so we learn and we understand. Then who knows, maybe we build up, maybe we need to scale up and we build a CAN network in the future. That would also be cool. So without further ado, I prepared the Mira board, and I'm also evolving in the sense where I would like to set up an environment where I do design or concept design, development, testing, manufacturing from to the beginning to the end, from concept to production. That's what this channel is all about. We're designing electronics, and we're learning as we go. So, a LIN network. LIN network. Or maybe I should rename it as a multi-node LIN system. LIN network. System. That's too much. LIN network. Multi-node LIN network. So maybe we start with some prerequisites. What do I write that? Prerequisites. And it would be good if there were some templates I could use. Hold on. Some type of no, I couldn't really find a good. So, prerequisites. I mean, first, for instance, I want to work. Need to go even further in. So here we have concept stage. And then further on, we have what do we have after concept? Initial rough design. I keep using rough. I don't want to use rough. Initial design. So from a concept stage until an initial design, and maybe I will reword that later. But I want to do we want to build a multi-node LIN network where we have a master controlling the slaves and outputting sensor data through outputting sensor data. Oh, it's okay. Let's make a nice short description of the whole system. So we want to build a multi-node LIN network where one node will act as the master, handling diagnostics and controlling or gatewaying information to the slaves. Handling diagnostics and communicating with the slaves, where every slave connects to either sensors or actuators that every slave connects to either where every slave connects to either sensors or actuators or both. Maybe. Like we try to generalize it a little bit. The MCU family selected should be the same. Or the nodes should be almost entirely the same, but with different tasks. So it's actually not the same at all. But So we can also design this, how that should look like. So master, something like this. So bring to front, no? LIN bus. So something like that. Very, very simple. Oops. Yeah, that's the concept. So we just want a master, so master PCB, and then slave 1 PCB, slave 2 PCB, slave 3. Or wait, I wanted to actually do like this. Slave N PCB. So what should a master do? The master shall include a way to let end users know the status of the nodes on the network. So for example, if it's connected, if it's on, so maybe power modes. i.e. power modes, fault states, so let's just say that the master should, I do this white, and then this bit thicker, so. Power mode indicators. Power mode indicators. And that's maybe a bit more for us. Hold on, let me think about this. I will lock this. Here maybe debug. Program. Power mode indicators. Maybe do core. So something like this. And then here. So network. Right here. LIN master. Oops. end user. It would be cool if it had a display. So some type of display. Sensor data. And for now, every node on the network will be powered from the same power supply, but we could also have, for example, the master powering the slaves as well. Maybe we should have that. That could be for another revision, maybe. Power management. Actually, I will put that. Like, for instance, here, power mode indicators just showing, you know, how the nodes are connected, if they're disconnected or something. So we get an indicator if all of the nodes are powered. Power mode. No, wait. Let's wait with that. Debug network. Display. Debugger or programmer, so we can set how the master should be controlling the nodes. So it will get, so if it will get data in here, so signals in LIN bus, then it will do some processing here, and then it will output output. That's it. And of course, this way, control. That's it. We're not going to make it more complicated than that. We start there and then we add to it. So the master will work like this. Very, very simple. Then we will do the slave. Now, since this is how I work, so I will color code them a little bit. I try to use good colors so it's not so freaking annoying, maybe. So blue is the master, red-ish is the slaves, and then on this one, we're looking inside the master. And on this side, we're looking inside the slave. So slave 1, it will also have, oops, some MCU, like power management and MCU. Then ideally not, we don't need any programmers or debugger on this, since we just wanna, or hold up. I guess we need it here too. And we basically need everything else. Or all of it. What am I doing? Okay, what am I doing? This is what I'm gonna do. I'm just gonna copy the whole thing, because you wanna modularize also. Use what we have, you know, the same MCU, the same power management. They're all powered from the same power supply. So we can use same solution, same debug solution, same MCU, everything. Same transceiver for compatibility. The only thing that is different here, we don't want a display. We want here maybe temperature sensor, for example. Sensors. And maybe here we have temperature, ambient light sensor. So a temperature and an ambient light sensor maybe. Should it do anything, this one? No, it shouldn't. We keep it simple. So we'll do like this. And we'll start with 2 nodes. I think this will be fun. I think this is a good no, I don't like that. I need to put them down here side by side, and then the master on top. And then what we want for the second slave, so this one, we want light module. Wait. RGB lights, for example. The actuator. Actuator. So we're sending signals from the master how these lights should be turned on, turned off, increased in intensity, stuff like that. And we use, for example, the ambient light to determine how light this should be. If this picks up darker lights, for example, we want brighter on this side. Very simple. We're gonna build it all from the ground up. From the ground up. So if this is slave 1, this is slave 2, we follow the same. And then the idea is that we can add on more on this network. I think you can have up to 15 nodes on one LIN network. So once again, everything is the same. The master, maybe we'll add a lot more to the master. We'll start with the master and keep that fairly simple. Then we make one of the slaves and we check, is that enough? Do we want anything more with one of the slaves, you know, or the master? And then we check, and we continue with the second. But the thing is, these PCBs will be simple, not so complex, and I think it will be a good exercise to do to build a network where you kind of consider a system solution, and you start with one master PCB that can do a lot of things, or a master node that can do a lot of things, but software-wise and also hardware, where you can have a display, for example, and display important information. So you have these things operating a little bit in the background, for example, with temperature and ambient light sensor. And then you have one that kind of shows something to the end user or changes the environment somehow. And then the master that kind of, you know, here you look at one display and you say, oh, okay, yeah, that node is working properly there, this one is working properly there. You get the point. Test, test, test. Yeah, my microphone is working good. But this is what I've been wanting to do for the longest time too, just build up these systems on my own and share it with the world. Share how you do it. Come up with cool, simple system solutions and build a community around the fact that we're designing electronics all the way from concept to production. We're gonna do concept stage work like I'm doing now, with working on some prerequisites, very abstract and very simple. You would get it maybe a lot more complex in a professional setting, but we're kind of just doing it a little bit on the go, which I think is fun because you consider the whole lifeline of the project. Okay, so the master, very simple. It's going to be a microcontroller, some DC-DC or LDO or something, a LIN transceiver, a debug port for a programmer, such as the ST-Link V2. And then we have a display that we can display some information. And we will also have some indicators, some lights, maybe some buttons that do certain things. Maybe we select modes for the slaves, how they should operate through inputs from the user. And of course, we're gonna have to take it a little bit on the go, or how to say, we can't be so strict. We're working from the comfort of our homes. We're not in a professional setting right now, so a lot of these things normally would go through a lot of different processes. But for example, we could jump straight in to to designing the master, for example, deciding which components should we have here. And we will come back to this probably a lot of times, deciding, okay, maybe for the master we should have also some type of sensor, or we should have another display. Maybe we should have display for each slave. Maybe we need more of this, more of that. But I think as a starting point, this is what we can have. So let's say that we have wait, this we don't need. RGB light and yeah. And you could argue that we don't even need on we don't even need a microcontroller on some of these PCBs. We could have LIN interface that also can handle, or LIN interface that can control these actuators, LEDs, or even sensors, communicating with sensors, taking in data, sending it on the LIN bus directly to the master, which is probably the most common way it's done with the LIN specifically. It all depends on if this MCU does more, I guess, and does more processing. But in the case where you don't really need to process anything in the slaves, we might remove the MCU completely and just have a LIN network. And we take away the debugger as well. How would that work? Is there a way to program here though? Maybe. Like program. I guess it is. Must be a way to program or send specific LIN signals to. Okay. But this is the things that we don't know, right? We don't know how. Oops. Like this out now. Hello. Can you still hear me? Yes. I think you can still hear me. Test. Yep. Okay, but maybe this is good enough. Maybe we put this down a little bit. We focus on the master. We want the master to communicate using LIN. So we don't really need to specify what happens on the LIN bus. How does the slaves communicate there? What do the slaves do? We don't really need to go that far. Let's start with creating a LIN master, which has a display, debug, some indicators. maybe. Let's skip that. So core functionality, power management, MCU, network, LIN, display sensor data, and debug for programming. Programming the node or the master. So let's say the master includes power management and a processing unit, which takes data from the LIN, transceiver, and outputs relevant information to the user via a display. The master features a debug interface in order to configure and program the master. The master PCB features a debug interface in order to configure and program the MCU. I will write MCU here too. So very simple. And let's start with that. There's no need to make things so complicated. So what I mean by power management is that we have a power supply connected to this node. So for the time being, yeah, we don't know so much about this power supply. Let's say it will just be a bench power supply, 12 volt. And then we need to handle that. So we'll get into the details later maybe. But and another LDO or DC-DC converter to get down to 5 volts or 3.3 volts for the MCU. And we have a LIN transceiver display. Yeah, very, very simple. Yeah, I'm so tempted to just go into looking for, or very tempted to just start with the schematic straight away. But I think what feels the best when you're designing electronics is knowing where you get power from. That's essential when you have, in this case, a node that you're designing and you're getting power from somewhere else. That can be different. It could be 12 volt. For example, in automotive setting, it could be 12 volt, 24 volt, 48 volt, perhaps. And you don't really know how it behaves, the power supply. Is it a steady state? Is there conditions where you need to account for something? And then I'm thinking more specifically on reverse polarity, load dumps, and transients. Everything that can happen, we need to account for that in the master. or in the node that we're building. So starting with the power supply feels like the best choice, knowing where that's the first input, right? If there's no power, there's no master doing anything on the LIN network or on the displays. Nothing is working. There's no lights on. So I think I want to start with that power management. So I put the slaves down here for a sec. And I just make like a let's wait with the slave nodes for now. So do something like this. Looks really stupid. We will wait with defining what the slaves do. All we know, let's say it like this, all we know is that this component should be the master. That's all we know. So make it a little bit clearer that all we know is that the node should be a master and slave information will come later. And that's fair, because we don't really know if cloud. All we know is that the node should be a master and slave information will come later. And that's pretty common, right? You have the definition of your component to be able to handle, you know, all the data coming from this LIN network. And you need to have the proper graphical interfaces or interfaces, indicators and everything to display that information or whatever you're doing with it. So right now we don't know what we're doing with it, but we can build the ECU thinking we're some type of gateway or just master that takes in all the data. We don't know what to do with the data yet. You know, some data could make some lamps glow or blink or something. Maybe we even have buttons sending over the network. We don't know yet. What will the slave nodes do? We'll put that a bit off to the side. I'll put this on the side here too. And I want to start with power management. But maybe I will also make myself a nice cup of tea. And then the debug part can be a bit on the side. That maybe should also just go, you know what? We'll make it even more simple. I'll just write debug here. So power management, MCU, and debug. User interface. Display. I do it like this. So core is the power management, MCU, debug. And here we go deeper into, you know, the concept. And we'll write it in plain words how this component should operate. And we'll make it very simple for us in the very beginning. It could be way more complex, I guess. We are getting power from an unknown source. But we know that we are getting 12 volts on the inputs. And that we need to handle common electrical protection or handle common electrical faults and conditions in order to protect our component. Something like that. So that tells us we're getting 12 volt on the input, but we don't really know so much more about it. What is this power supply doing? Is it always 12 volt, or is it varying? Is it at some points lower or higher? And what does that mean for our component? We need to make sure that it operates properly in every case. So move it a bit more off to the side. So common electrical faults then. So we need to handle, for example, over voltage, inrush, current, reverse polarity. Yeah. The MCU will be the master node, and it needs to process some data from the other nodes on the LIN network. Details unknown. And it also needs to handle the diagnostics of the other nodes on the network. It should also be possible to debug the master. LIN will be the main communication interface between the nodes, or it's basically just the slaves either reporting some information or being told what to do. So through a scheduling table, which we'll come back to later. But first off, LIN will be the main communication interface between the nodes. That's it. Lastly, some important information shall be presented to the end user. PR just came with a good idea. What if this information is critical? It absolutely has to be correct. It needs to which has to be end-to-end protected. Ba-da-da-da. So imagine yourself someone that really needs it, someone that really needs some type of information that it can depend on. It's a matter of life or death, perhaps. And they're looking at this display, and whatever comes there, they have to make a split second decision on what to do. And if that information is somehow corrupted, it's not correct, it's half of the truth, and that's no good. So let's say that it has to be end-to-end protected, just for fun, just to spice things up a bit. Yeah. Well. Yeah. I don't want to make it too complicated either, right? But in order to create PCBs from concepts to production, you have to think a little bit about these things, how everything should work, not if you start in one end, what will it be in the end, really? Like if you just jump straight into it, you select all kinds of components, you throw it on a schematic, you connect them, you plug them in, you kind of impaired yourself to the best possible solution. But if you start with, for example, power management, understanding 100% how the power of this component is handled, how is it getting powered, when is it getting powered, it can handle all fault stages that happens or any type of conditions. We know we're safe. And if anything happens on that side, you know you're safe. The rest of it. And then you can continue with the microcontroller, and you select the one you want, the one you want to work with, and you start getting a feel for what's going to happen next, instead of jumping straight into things and just selecting, going crazy, which is sometimes very tempting to do. But that's not what this channel is about. We want to design electronics from concept to production, and this is how you do it. I will take a 5-minute break. I will be right back. Okay. Oi. Oi. Oi, oi, oi. Da, 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 da. So starting with power management. Yeah, just thinking a bit about power management. let's say that normal or typical inputs. Let's make a table. Maybe rather just a grid. So input conditions. And we say that typical voltage, voltage, or operating voltage should be 12 volts. Right? Right. So like this. Um, let's, for the sake of simplicity, just say that the operating voltage is 12 volts. So it's just a bench power supply. Shall okay, take this away. 12 volt input. 12 volt input over voltage protection. Over current protection. And then ESD. Or reverse polarity. Reverse polarity protection. So we'll have overcurrent first. So maybe fuse or something. Put that first. Then we have reverse polarity. surge / ESD protection, and an EMI filter. EMI filter. Bulk capacitor. And then a DC-DC. So that could be good. So over current, so we have a, yeah, the current we're working on, and we set a trip value or choose a fuse with a certain trip value. So and so much current, we trip the fuse. Then we have reverse polarity protection. So just a diode or a P-channel MOSFET in order to handle it if anyone is, let's say we have a prototype board, we have two two-pin screw terminal, and someone puts the power on the opposite side. Reverse polarity. So we stop that from happening. Surge, ESD protection, so just a TVS diode to ground, EMI filter, because we're, let's say it's a noisy input. I don't know, I'm not sure what I put behind the EMI filter so much. Bulk capacitor. I guess it's not really a protection though. I guess we can kind of remove those and then go to this later, right? Yeah, but let's start with those four. So we have a 12 volt input. We want a fuse, so a polyfuse, for example. Self-resetting. Reverse polarity protection, either a diode, maybe just a diode. Just keep it simple. Surge ESD, so TVS diode. To ground, EMI filter, so an inductor or something. let's see how that would look like. So if we, once again, we draw it up, we write on power management. We know that we're getting 12 volts on the inputs. Are we getting ground also? Make that. So like that. And we would like fuse. What did I say? Reverse polarity. And ESD. Connector. So kind of like this. So we have a connector to fuse, to reverse polarity protection, to ESD, and then we have the rest of the circuit. Kind of like this. Rest. Oops. This I would just take away. I'm also not sure if we need wait. like that either. Trying to draw it up so it's a bit nicer to see. Power and ground. Safe, right? That's the goal. 24, 24. So the goal is to take power and ground from an unknown source. We said that it's a 12 volt supply. Thank you for that like, by the way. Someone put a like on the stream. I appreciate it. Hope you're doing all right. Let me know in the chat what's going on, where you're from, and what brought you to this channel. Thank you for that like. Please subscribe to the channel too if you like this type of content. We're designing electronics from concept stage to production. So if you just tuned in, we're designing a LIN network. We're currently working on the master node, and we're starting with power management because it's such an important thing when doing component design, understanding how your component is powered, and that you know that you have all electrical conditions or faults covered. So for example, we said we need to handle common electrical faults and conditions in order to protect our components. So we listed up overcurrent protection, reverse polarity protection, surge or ESD protection, and an EMI filter, which I didn't include right now because I thought maybe it's a little bit too much to add that to right now. It's an aspect. Okay, hey Aslan, greetings all the way from Turkey. Cool to have you here. Feel free to interrupt me. I'm just talking and talking. And if anyone shows up, yeah, they can listen or they can ask me questions. Cool that I ended up in your feed. So hope you enjoy the channel. Hope you enjoy electronics. That's what we're doing here. Building. Currently, we're in a concept stage. So you've seen the title for this stream is building a complete LIN network. So, but we're kind of taking it, biting off a little bit at a time. So currently we're working on the master on the LIN network and taking again the most important thing, protecting your components. So here we're just doing some system design, some concept design before we go into KiCad in the future, doing more design, doing more proper design, schematics, layout, and then hopefully go all the way to production and order these components and do some testing with real life applications. And I invite my viewers to join and kind of learn a thing or two about electronics, but also help design the circuit as well. I think that's pretty cool. So glad to have you here. And yeah, feel free to ask any questions if you would like. I need to remember to drink my tea, so I'll have a break now. let's say unsafe. Or noisy. No, can't really say that. Just because it might have over voltage or something, it doesn't mean that it's unsafe. We just have to, these are input conditions. We need to handle it either way. We're the new component in some type of environment. We need to be able to have the necessary circuitry in order to live and thrive in that environment. So just write power and ground again. So it goes into the connector. We have a fuse that handles over current, so it will trip if we're drawing too much. Then reverse polarity in case we switch power and ground on our connector. So maybe in the beginning we'll start with just screw terminals or something like that. And then also an ESD in case we're sending off surges in the 1000 kilovolt range to ground. Safe 12 volt. And here we could use like a hard fuse, one that doesn't reset, but that's not really, I don't know, do people, what cases do you use that? Might be a bit older to use that. You also have these poly fuses, which is self-resetting. So it will basically, when it's too much current. Wait, how does a polyfuse work again? When it's too much current, it got high impedance, maybe. So it's high resistance, so it's not. Okay, I need to Google. Let's say poly. Yeah, it drastically increases its electrical resistance during an overcurrent event, acting like a self-resetting circuit breaker. So I thought that is a nice protection feature to have. You draw too much current, it increases its impedance, and it trips. So there's no. When excess current flows, the polymer heats up, expands, and changes from a crystalline to an amorphous state, breaking the connective paths. So it's essentially an open circuit. Dramatically raises resistance and limits current. Once the fault is cleared, the device cools, the polymer returns to its original low resistance crystalline state, restoring conductivity. Cool. Reverse polarity can just be a diode. And then the ESD TVS diode. So in the case where we got very high voltage, we send that straight to ground, protecting the rest of our circuit. That can be in surge events, like ESD events. Not really continuous over voltage. So if someone would crank up the power supply to more than 12 volts, so we have defined we'll have 12 volt on the input. We haven't really said yes, it is normally 12 volt, but in some cases there could be a fault or conditions that would put that up to 24 volt or 36 or something. We haven't defined that. We're skipping that for now. Because for our test, we'll just use a bench power supply, so we will set it to 12. But for example, an automotive environment, you can have different conditions where you have higher or lower voltage. Yeah. And then this would, of course, go to, I think now I could add below here. So this will go down to a bulk capacitor or just a DC-DC or regulator. Regulator, LDO or DC-DC. So it will be from this part, the 12 volts, in order for it to power our MCU. And that's how we should work. We secure power first, making sure that here we got safe 12 volt to work with, and then a regulator. So if anything happens here, the rest of our circuit is fine. Then we got the regulator in order to, go down to 3.3 volt or 5 volt for the microcontroller. Yeah, we have a very simple component, so we have a very simple component. Luckily, we don't have a lot of power rails. Like we don't need 12 volt to 5 volt down to 3.3, 1.8, 1.2, stuff like that. That's for the future. So in the future, we'll also work on way more complex stuff, but right now, simple. Simple is key in order to learn to develop and learn to not talk so damn much like I do. Learn to just go with it. So regulator. Oops. Continuous. So from here, I try to keep this space a little bit, I like having a bit of room. Maybe I should do like this then. And I put it here instead. Yeah. And here we can also make it very complex and say, is it fine to have a linear dropout regulator from 12 volt to 3.3 volt? And probably not. You would do it if you really had to do it, but you waste so much energy in the form of heat, because that's how a linear dropout regulator works. You take If you take a 12 volt input and you want 3.3 output, I haven't prepared a very good explanation for this, but you can say the voltage drop across, so the input to the output is so big that the way you regulate that gap becomes so big, and since the LDO works or is resistive, resistive in a sense. Damn. Some real experts would tell me right now. Shape up. But yeah, so it's resistive. The gap is too big. It's or the gap is very big. It's resistive in a sense. So you lose energy in the form of heat. So you get a very red component on the PCB, which should maybe do something with the efficiency of this as well. Maybe. So in the case where you have a very high drop from 12 volts down to 3.3 or 5 volt, you probably want to use a DC DC. So that's what we're gonna do. One that takes a fairly stable 12 volts, so we're not accounting for higher than that. Like I just mentioned before, we'll use a bench power supply. And we're probably fine with just using 3.3. So this is how I kind of look at it. We have more red for the more unprotected 12 volt supply, then you have a slighter redder indicating safe. And then quite light red indicating 3.3. And it's a good way to, when you're working on electronics, to kind of split things up into modules or tiny boxes that you will work with. So here I could actually regulation, rather. Power management continuous regulation. So we have a step down converter then, going from 12 volts to 3.3 to the MCU. And now I'm contemplating if I should already start a little bit with schematic, because this is on a high level. This is a high level system design. We know that on the PCB we need to have a connector in order to power this, give it power and a ground connection. And we need fuse for overcurrent protection, reverse polarity protection diode, for example, and search ESD protection. Let's scratch this for now. And also not make it red anymore. It's an eyesore. And then the regulation. Because, for example, when you're working with this part, you clearly know what to expect. From 12 volts, you need to handle something like we have specified here, and then this part is kind of, you don't need to worry about what happened before, right? So when you're doing your design, you only focus on the regulation part. That's the task at hand. Yeah. In this case, maybe we don't need a 5-volt rail. I'm just thinking to keep it simple in the beginning. I will make more, we'll add to it for sure. I mean, it could be that this display, I haven't worked so much with displays, so it could be that the most common displays on the market uses 5 volts, and there you go, then we need 5 volts. And then we could, for instance, say that we use a DC-DC to 5 volt, and then from this 5 volt we go to an LDO. To 3.3 volts. And then this goes to the display, and then you have, maybe enabling signals or the driver itself from the MCU. Control it with the MCU, but you have the rail at least to power the display. That could be something. Good point. Like I just googled real quickly. I can put it here. LCD module, for example. Operating supply voltage 2.8. I really haven't worked a lot with displays, so I couldn't tell you, but going back to what I defined the masters, I do this very just on the go, just trying to, I haven't really prepared the whole system. That way I don't even know what the slaves in the system will do, what type of information they will send. And that's something I invite the viewers to even come up with if they have a good idea or if they want to see something. But yeah, the master includes power management and MCU, which takes data from the LIN transceiver and outputs relevant information to the user via display. The master PCB features a debug interface. Yeah. So that's all I know. It's just a display. I don't know how it's powered, what type of information is there. Yeah, that's a good idea. You add, of course, another components, another layer or another step, but it's very common too. a lot of things use 5 volt and of course 3.3 volt, but it's good to have that rail, I think. Let's see, just Google some different LEDs. I mean, OLED screens, for example. I can only find modules, but maybe OLED display. Was this the one I was looking at? 2.5 to 3.3. I just thought for a LIN network, it would be cool if the master had a display that I, for example, could monitor, and I could place LIN nodes around the room, which has specific tasks, whether they have some sensors included, monitoring ambient lighting, or reading the temperature in the room, or other actuators. Maybe have a button across the room that I press when I enter the room, and a controller sitting maybe right in front of me here. I could monitor everything, just as a fun little project. Who knows what it will turn into. Let's look at OLED drivers or displays, sorry. Just curious how expensive these are. Okay, 15.6-inch touch display. Maybe not that one. It's a bit too big. We don't really need to make it too complex. We can just have that extra rail. I think it will pay off in the end. We're designing a master, So, and I talked about this before. We don't really know. So all we know is that the node should be a master and slave information will come later. That was kind of how I wanted to start. Whereas I don't know what the slaves will give me. So I will add functionality later when we define here what they should do. So maybe we do need a 5 volt rail. Okay, enough jibber jabber. But I actually soon have to end the stream. It's getting late, I need to start the process. But I will stream again tomorrow, of course. Or, of course, I try to, the goal is to stream Monday to Thursdays after everything is handled at home. So that could be sometimes as early as maybe 5, 6 I start, and then I go until late, until around this time, around 10 o'clock. Yes, so until around 10 o'clock is the ideal, so I'm kind of a bit on overtime. But I started a bit late today, so I've been streaming for 2 hours now, and I consider that as a minimum. That's the minimum I want to do every day that I stream. And of course we're in holiday time, so I won't be streaming during the holidays, but I will continue afterwards. So yeah, we're starting a new project, building a complete LIN network. Starting with the master, and then we add on and modularize the slaves as well. If we can have this whole room set up in the future. Previously, I worked on a AC/DC switch mode power supply design that I put on pause for the time being. I really enjoy power electronics, so I'm gonna be working a lot more with that as well. And I'll touch up on a lot of industries. So now we're a bit in automotive. Then who knows where we go next. Really would like to get into audio, a bit more radio frequency, RF designs. So yeah, a lot of cool things. Thank you for tuning in. Really appreciate it. It's really cool to get fellow enthusiasts, engineers, hobbyists, or whatever coming in, building up this community of like-minded folks. Yeah, feel free to drop by at any time. I'll be here. Okay. I'm getting tired. Yeah, thank you for tuning in, and I will end the stream right now actually. Go finish my tea and then go to bed. Wish you all the best, and until next time, bye bye.